Hi, this is part 3 of a video series, how to create and control a COMSOL model from MATLAB. If you haven't watched part 1 and part 2, I suggest that you first watch them and then continue watching this video. In part 1, I described the problem and then we made a special case of that problem in COMSOL and saved it as mfile. So this is the mfile that we saved. In part 2, we learned how to establish connection between MATLAB and COMSOL server. And now in this part, we will look at the commands available in this base model, and we will utilize them to create our own generalized function. Okay, so the first thing that we want to do is to create a new function. Because the only variable that we have in this problem is the radius of the circle, so our function should have one input, which is rin. This is mgh is my name, and then the output of the function is the electric field on the perimeter of the circle. So for any given r, basically we calculate, and then we calculate the electric field on the perimeter of the circle. We find its maximum, and we compare it with the threshold electric field. And if necessary, we repeat the process until we find the maximum value of r. So now first I'm going to save this function. At this moment, however, I do not need to create a full function. I want to only create a part that is necessary for creating the COMSOL model. And at the end, I will connect it to this function. So I comment this part. Now, if you look at the test model, the base model that we made, many part of this test model is actually exactly the same as what we need. So here we have, for example, import of the library, the name of the model, the folder. We want to create a new model. This is to have the geometry, to mesh, and then the physics is electrostatic. We created a study. The study is stationary, and we want to perform that study on the electrostatic physics. So all these parts will not change in our generalized model. So I have to copy them directly into this new function. Okay. The next part is to create a geometry. So we can see that this line is actually to create a rectangle, and here we set the size of the rectangle. Basically one side is 3 and one side is 1. And then with this one we create that rectangle. So all of these 3 lines we have to copy directly, no change, because the background rectangle does not change in our model. One thing to notice is that because I clicked 2 times to create that rectangle, you can see that I have 2 lines here, the same thing, but only one of them is enough to create the rectangle. So I just copy all of them here. Okay, now the next line is actually to create a circle, but then right after that I created a parameter. So maybe it's better that I create this parameter before creating the geometry, so to have some order. So here I create the parameter. This is how to create the rectangle. And then I can copy this line, which is creating the circle. And also these few more lines to create the, to set the radius of the circle equal to r, which is this parameter, and the position of the circle, and to create the circle, and furthermore to create the whole geometry. So I just copy all of these because these are what we need. Okay, so at this stage we can notice that here we should make some modification, because the radius that this circle has here, it's fixed at 0.2, but what we really want is that this radius should come from the input of the function. So at this moment I just define this input equal to some number, maybe 0.2. So what I'm going to do is that we have to basically, instead of putting 0.2 here, we should give this radius. But this radius is a number. So what we have to do, we have to give a string here, because this one is right now a string. So I have to convert this this numerical value into a string value and then put it here. So for example, if I define rin, let's say rin, I don't know, 1 is equal to num to a string rin Then what I can do is that I can give this parameter RIN1 here instead of that. So right now, whatever RIN that comes from the input function will, at the end I have to remove this one, will come here, it becomes a string, and so we have the string value, it will come here, and then basically we can create different circles. Okay, so now let us check this model until here. So for example, if I run this model, the model is already created, and then we can connect to this. Okay, so this is the model that we have created. We only created the geometry. So one rectangle, one circle, and also we have parameter r, which in this case it sets to be 0.2. But what I can do is that if I let's say I want to have 0.3, as I explained in part 2, we have to change the name of this model to avoid error. So now if I run this one, then a new model will be created because it doesn't have any other parts, so it's very quick. And now if I import this one, obviously I will have a radius, I will have a circle with radius 0.3. So far what we have done, we have created the geometry as we want, and also we parameterize the radius, which then we can receive it from the input of the function. Now we have to continue building the mesh and the material and other parts. Before I continue making mesh and other parts, I want to mention that we can also observe the geometry directly in MATLAB. So to do so, we have to use this command, mphgeom, and then this is model. So the model is here. So now if I run this model, we can see that we can see the geometry in the MATLAB figure. Now if I change the radius, let's say I make it 0.2, you will see it directly here. So we do not need to connect to COMSOL graphical interface to see the geometry. You can see it directly in MATLAB. Okay, so now I continue with the next part, which is setting material, because in this case we assume that the material everywhere is vacuum, so permittivity is 1, nothing will change. Even if I change the radius, still the material is the same. So I actually have to copy these two lines directly into my new function. Okay. The next part is the boundaries. So we create the ground boundary and we assign boundary number 1, 2, 3, 4 to ground. Also we create electric potential and we assign boundary number 5, 6, 7, 8 to electric potential. And then this line is basically we set the voltage to 1 volt. Now one thing to notice is that the index of these boundaries in this problem, the indexes would be fixed no matter what kind of radius we use. So even if I use 0.2 meter or if I use 0.3, 0.4, it doesn't matter. Still the outer rectangle will get the indexes of 1, 2, 3, 4, and the circle will get the index of 5, 6, 7, 8. And this, so we assign correct boundaries to ground and also correct boundaries to electric potential. But in certain problems, it can happen that when you change the input parameter, the numbering of the boundaries will be different. So you must be very careful not to directly assign like ground to these boundaries and potential to these boundaries, because maybe these are the wrong boundaries when the input parameter changes. So this is some other topic which is a little bit more advanced. I will cover it in another video and show you examples what happens when the input parameter changes. But in this stage, nothing will change in our model because the model is very simple. So what I have to do, I have to copy this part into my new model. And also that one line which sets the voltage to 1 volt. Okay. So the next step is basically to set the mesh. So I can copy this line and also create the mesh. So if I run this model right now, so okay, I have the geometry, I can see it in MATLAB. I can also connect with COMSOL to the model. And you can see I also have the mesh. We can also see the mesh in MATLAB if we want. So the mesh command is very similar to what we have there. So instead of geom, we have mesh here. I change the name of this model, and then if I run it, so you can see that I have the mesh here in MATLAB figure. So what I can do, I can basically give one figure here, so figure 1, and this one I give it figure 2, such that we can see the both of them. Basically, we have the geometry, we have the mesh. We can notice that the parameter of this auto mesh size is 1 here. This means that the mesh is extremely fine. If I increase this number, let's say to 4, then the mesh will be coarser, as you can see here. Now this is the default mesh setting by COMSOL, but at the end you know that we decided to make a custom mesh because the results that we got was not very smooth. So at the end, actually, we do not need to use these lines in our code. We will replace them with the custom mesh that we made. So if I go back to this test function, so up to here we have done it. But then if you remember when we made the COMSOL model, at this moment, we actually run the model. We then evaluated the electric field on the perimeter of the circle. We saw that the electric field was not very smooth, so we decided to create a better mesh. So here is the section that is related to mesh. We created an edge mesh, and then we assigned boundaries 5, 6, 7, 8, which are the boundaries of the circle, to this edge mesh. Then we created a size, and we decided to use custom parameter. And then we decided to change the maximum size of the mesh, and we set it to 0.005. And then we created that edge mesh. And after that, we created a free triangle, and then we performed that free triangle. So all of these lines are actually the custom mesh that we made. And now I have to copy all of them into my new model. Actually, I do not need anymore these 2 lines. Okay, so this will be the mesh setting, which again, probably we do not need to change that mesh setting when the radius of the circle changes. So we have pretty good mesh close to the boundaries, and this will give us a very smooth curve at the end. Okay, so now we are done with the mesh. We move to the next part, which is creating a solution. Because I haven't changed anything related to solver setting, and no matter what value of R we have, in this case the default setting by COMSOL is good enough. So I'm just going to copy every part related to solution directly in my new function. These are all the sections which comes here. Now, when we make a model directly in COMSOL, for example in electrostatic, by default 2D surface plot of electric potential will be given in the result setting. So this is the surface plot of electric potential. But actually we do not need to create this because I'm not interested in potential distribution in this case. But if you look at the commands, we see that, okay, so we create a 2D plot and we change the label to electric potential, and basically the data comes from dataset 1, which we have created before, and then it's surface plot. So this is the setting of the color table, and basically we create this 2D surface plot with this code. And this one is the line that actually perform the solution. Okay, so now you notice that I manually created a 2D surface plot for electric field. So I want to copy this part into my function, even though I do not need it. So here is the 2D plot. This is the surface plot, and then it's the electric field, norm of the electric field, and we run it. So these two are the same, so I'm just copy one of them. I copy both of them, and then I delete one. So here we have the, I do not need this one. Basically, with these few lines of code, I created 2D surface plot for electric field. And after that, I created a 1D plot. This is a 1D plot. And then I created a line graph. Before I finalized that one, I created a data set. So these two lines are basically an edge data set. So I first copied them. Okay. So here I have the edge data set, and the edges are basically the perimeter of the circle. So then I create this 1D line graph, which would be here. This part is not necessary at this moment, but then instead I will copy all of these few lines. Okay. So what we have done so far is that we created a solution. We have also added a 2D surface plot of electric field into our results. Also, we created a data set, and we added a 1D plot over that data set. Now, if I run this model, let me change the name of the model. So, okay, model is already done. So I'm just gonna connect COMSOL to this model. If I go to result, you can see that I have 2D surface plot of electric field. Also, I have 1D plot of electric field over the perimeter of the circle. But again, you notice that the magnitude of electric field is half of the maximum electric field in the surface plot, because in the original file, in this test1, you remember that at the end, I changed the value of electric field to 2 times for this line graph. So I have to actually do that one also here. So instead of expression is norm of electric field, I have to put 2 times norm of electric field. Okay. So when I run the model, and if I connect COMSOL to that model, basically in the results, again, we have the surface graph, and also we have the line graph over the perimeter of the circle, and the value is the correct value. It's just above the perimeter of the circle. All right. So now we have the model, but you notice that this line graph, we have it in COMSOL. I do not have directly access to that line graph here in the MATLAB code. Now I'm going to show you how to extract the data of that 1D line graph here in MATLAB. But before that, I want to show you how to plot 2D surface plot and also 1D graph here in MATLAB. To do so, we have to use this command, which is basically mphplot model, and then here is the tag. pg2 is the tag of surface plot of electric field that we have created before. And then this range number equal to 1 means that we want to have the color bar. So again, let me add another figure here, figure 3. So if I run this model, okay, I should change the name. Okay, so I have the 2D plot, I have the mesh, and I have the 2D surface plot of the electric field. I can do the same thing for the line graph. So let me add this one here. This one should be PG3. And then another figure 4 maybe. So if I run this one, this is the geometry, here is the mesh, this is 2D surface plot of electric field, and this is 1D plot of the electric field over the perimeter of the circle. 2 times than that. Okay, so we already know how to plot them, but how to get the data of these one? So in order to do that, what we have to do is to, let's say I name this as data. So all the information related to this struct element will be now transferred to data, and we can see that in workspace. If I run this again. Now if you look at the workspace, we can see that here there is a data element. If I open it, it's 1 by 1 cell. If I open it again, it's a 1 by 1 struct element. And if I open it again, we see all the information that is available in this struct element. Now this P is basically the information related to the arc length. So we have this arc length, and this D is the magnitude of electric field that we evaluated. In this case, it's 2 times the magnitude of electric field. So now I can actually plot this one in MATLAB. So basically we have data, and then we have 1 and 1. So again 1 and 1. So dot P versus dot D, and then let us plot it with dot. So now if I plot this one, you can see that we have this line plot here in MATLAB. So what we have to actually extract is these two vector, so this one and the next one, and actually give that one out as the parameters of the electric field on this perimeter. So what I'm going to do, I'm going to make a matrix. So E underline P, this is the output, is equal to basically this one, and then for the next one we have, this is D, but that one you have to transpose it. We have to transpose it because you can see here that P is 1, a vector of 1 row and 1012 column, but this one is the opposite way, so we have to do a transposition. Okay, so now if I run this again, okay, everything is there, but here also we have the EP in this place. So now I can actually plot, let's say if I want, I can plot EP the first row versus EP the second row, and then let us plot it with red. So this would be the result. So of course when we run the main function and we call this function, we have to calculate the maximum value of this second row of this EP, because that is the magnitude of the electric field. So now what I'm going to do, I'm going to go here and I'm going to enable this function. So basically now we can call this function from external window, and we give the input radius, and what we receive is the EP. So now I also comment this one. All right, so now the function is ready. So let us test it first. So I make this function is test. Basically, let's see if I do mgh 0.2, for example. So I call it a is equal mgh 0.2, and I name it as final. So now if I run this function, basically what happens, we see that all the parts will be created. We have the electric field, and also we will get this A here. But of course, I am not interested really on the electric field on all the perimeter. I'm interested in maximum value. So what I have to do is to get basically now I can define max A, the second row of A. So this would be A1, let's say. And I can change these numbers. Let's say if I put it 0.3, what happens? So we have bigger circle, here would be bigger, everything would be different, and this one is different. And if I see, for example, value of A1, this maximum electric field right now is 6, which is a little bit higher than what we wanted, because the threshold for us was 5. So now, as a simple approach, what I can do, I can basically decrease the radius. So this is the radius that we have. I can decrease that radius, and from this 0.3, I can decrease it gradually until the maximum electric field reaches to 5 volt per meter. Okay, so to do so, I can introduce a for loop for I is equal to 1 to 20, let's say. So then we evaluate this A. So the radius, we decrease it gradually, so I divided by 100, let's say. We calculate the maximum electric field, and now we say that if A1 is less than 5, then we break, and basically we say our max is equal to 0.3 minus I divided by 100. So now if I run this little code, then basically the radius will be gradually decreased, and every time we calculate the maximum electric field over the perimeter of the circle, and then whenever it's less than 5 volt per meter, then it stops, and that gives us the radius. So let us do this. So now if you really want to do such type of problem, you have to obviously comment out all these figures and plots, because they will take some time to plot them. But in this case, I want to show you how does it work, so I left them there. You can see that as the radius of this circle decreases, the maximum magnitude of the electric field is decreasing, and eventually it will reach to a value which is below 5. So at that point the model will stop, and basically we find the maximum radius of the circle such that the electric field will be less than 5 volt per meter, and that is basically here, which we get 0.21 meter. Now obviously if we wanted to have more resolution, we could actually divide this I to 1000, but then instead would take much more longer time to do this analysis. Okay, so this is end of part 3, which is actually the end of this video series. In the future, I will make a few more videos relevant to this topic, and we will discuss more advanced issues and features related to this topic. Alright, bye!